between the graph of the function y equals 6x minus x squared and the x-axis for x is greater than or equal to 0 and less than or equal to 6. Okay, so it says partition that interval, 0 to 6, into 4 subintervals and show the 4 rectangles that L, R, A, M. Now this is just this particular textbook's way of saying rectangles generated with the left edge of each subinterval. So you might remember we drew some pictures. Let me. You remember this now? This will come back. It's been a while. We haven't talked about this stuff in just a little bit. Okay, so let's look at this. Now, here's the kind of picture that we drew a while ago. We said that if we've got some, remember this, if we have some function f, and we're going to divide this thing up from like a to b, we're going to divide this up into a certain number of rectangles. I'll just draw a couple of them here. Let's say here are the first 2 subintervals. Now, if we're using left rectangles in this case, are they going to be inscribed or circumscribed? Inscribed, right? They're going to be inside of the function. The left, if I look at the left edge of each interval, so for the first interval, right? The first interval is the one that starts here and ends there, right? So the left edge of that interval, the function is that high at the left edge. So that's defining the height of the rectangle. So that's the rectangle that we would create. See what I'm saying? For the next rectangle, its left edge would be right there. So that's going to be the height, at that value of x, that's the height of the function. So that determines the next rectangle. So, and we talked about, we didn't spend a ton of time on this, but we talked about this a little bit. Remember, we made some generalizations. We said that if a function is monotonic increasing, so if it's always increasing, then the left edge would always represent an underestimate. That's going to be the inscribed rectangles, and the right edge would be the circumscribed rectangles, right? And it'd be the opposite if it were a decreasing function, right? So then if we look at our choices here for this one, first of all it says, well, choose the correct graph of the function. Well, we're just graphing the parabola, right? So that's just a matter of, that's just some Algebra 2 practice. I wish I could make this bigger.
So all you gotta do is look at the equation and give you
yeah,
function.
Exactly. Yeah, so you probably can't read that, but I'll rewrite it here. So the original function is just y equals 6x minus x squared. And so, it's just a matter, probably on this one, what would be the easiest way? Let's just do a really, really quick review of a little bit of analysis or Algebra 2 stuff here. So if we have y equals 6x minus x squared, what would be the easiest way to graph that thing? To sketch it. Because you don't have the graphing calculators on this one. But you don't need them. You could always make a t-table, but you don't need to.
Is it upside down?
It's okay, it's what do you mean by upside down? You're on something there.
It's concave down.
It's concave down, right, exactly, yeah. Because a is negative, isn't it? Probably maybe write it in standard form would be helpful. So if we wrote that like negative x squared plus 6x, we can see that it opens down. What else? How could we?
Moves to the. Nope,
And then it goes to the.
Maybe this is just a good opportunity for calculus. Is a great forum for doing like mini reviews. Everything just kind of comes together here with all the stuff you've done in the past.
It runs to the 6 on the x-axis.
So, okay, yeah. So why not? If you go back to think back to your Algebra 2 class. It's been a little while, but we had a couple of ways that were real convenient representations of quadratic functions, right? We had a vertex form. Do you remember what vertex form was? Couple things. I didn't have a lot of you in Algebra 2, so I don't know what was, I just don't know what was emphasized and what wasn't. I'm sure it was great, but I just don't know what was what you guys talked about when. A couple things that I'm probably gonna risk repeating myself here, but stuff that you've already heard. But you know that whenever you talk about a vertex for a function, what are typically the symbols we use to represent the coordinates of the vertex?
X and
No?
0, 0.
No, okay, maybe H and K,
Oh.
right? Does that make sense? So whenever you're talking about a vertex of any kind of a function that has a vertex, H and K is typically the way that we describe the coordinates of the vertex. So in vertex form, we know that that's the vertex. And it's just y equals, we always have an a out there that's our multiplier. It tells you stretches the function or shrinks it vertically, right? That's the job of a. In this case, it's -1, right? And then if it's in vertex form, remember this one? X
Minus H.
minus h squared plus k, right? Okay, now, we're not gonna need that one here, but I just want, and these are good to know. It's good to be aware of these. So that's one of our special forms of a quadratic function that's very functional to us. I mean, it's one where we can look at this, and by inspection we can see the coordinates of the vertex and a, and so it's a really good way. It's very, very simple to go from this form of a quadratic function to a working sketch of the graph, because you can see the vertex. That's the most important point. You can see if it opens up or down. Oftentimes that's all you need. Okay, the other one we looked at was factored form or intercepts form, right? A times, and then we just factor it, right? And this is one at the time in Algebra 2, it probably seemed like some kind of a mysterious, weird formula, but all it is just factoring it using the zero product property. How does this factor? I mean, technically, this one, you might remember, I think in our textbooks, it was written like that. But how does this one factor up here? What can I factor out?
X.
An x, and another rule that's always good to remember too.
Negative X.
Yeah, you always want to take out the coefficient of the leading term. You want to include that with, or the sign, sorry, the sign of the leading term should get included in the greatest common factor. If it's positive, it will, that's just positive, but in this case it's negative. So we'd have a negative x times, okay, and that's factored form, so what are my zeros? 0 and 0 and 6, and it opens down, right? You see my point? So if you look at it that way, it's really easy. Now that pinpoints this function. Which one is it? Right there, isn't it? Right? Make sense? And you could have done that a variety of ways, but that's probably the easiest and best way to pin down the graph right away. Okay, so now which of these, it would be the appropriate graph for the left rectangle estimation or approximation? Do you see that it's this one? Let me make this bigger so you can kind of see why that's the case. Yeah, because it's based on the left edge, isn't it? So if we look at the first subinterval, we've got this thing broken up into 1, 2, 3, 4 subintervals. And if you look at this first one, well, the height of the curve at the left edge there is 0, right? And which we get. There's our 0 height rectangle right there. Second subinterval, the left edge, there's the left edge. That determines the height of the second one, etc. Right? Is that taking some of the mystery out of this? Does that make sense how they're getting these answers? Okay. Questions? Okay. And I knew there were going to be questions on these because there's some terminology there that's a little bit new to you, like the LRAM. And if you ever run into that stuff, just ask. Ask for clarification. Yeah.
Is it always going to be based on the left edge? Is that
No, it's not. There are a variety of ways to do it. In fact, most of the time, remember which is the preferred side, probably the easiest side to work with. The right edge, yeah. So typically, we'll work with the right edge, especially if we're going to take a limit and let those things, let those things shrink to 0.
So why is it the left edge?
Well, because you can use the left. It doesn't really make any difference. You can use the left edge.
Okay.
Yeah.
Stands for left.
Yeah, right there. That stands for left.
Okay.
Yeah. Okay, and then they want you to actually make that calculation. Now, this is not a calculus thing, right? Making that calculation literally just means, okay, we're going to, I mean, there aren't any numbers on here, but what you would do is you would just say, okay, so this second rectangle, well, what is gonna be the width of the rectangle? You know, delta x equals what? How do we calculate it in general? B minus a is the width of the interval, right? Divided by n, sure. And in this case, we went from 0 to 6, and we used 4 intervals, right? So we would have gotten delta x equals 6 minus 0 over 4, which is 3/2.
Oh, wait, so your interval is on top, and then your forward is your number of triangles?
Well, they told us to make 4 rectangles.
Or, that's a triangle.
Yeah, they're going to divide it into 4 subintervals.
Okay, gotcha.
Okay, so then all we would do, if we want to calculate the heights of these things, or calculate the areas, well, we know that this right here is 1.5, and so the height of this is just going to be f of 1.5, isn't it? Right? Put 1.5 in the function to see how big that is. That height times 1.5 gives you the area of the first rectangle. Just add them up, right? And we went a little further with the, when we looked at these, we talked about how we could use sigma notation and add these things up, add up big sums of these things. I've kind of made the decision here that as I was sitting down to make these tests, I thought, okay, we got really 2 ways we can go with this. We can either sort of go back and review that a little bit and focus, but instead I'm thinking I'd rather not do that. I'd rather get a little further with techniques of integration, and maybe at the end we'll go back and take a little look at that. But I think we've spent enough time on this, being as you never really do it. Really what you end up doing is calculus, and this isn't really calculus. Now we know the trick. Right now we know that we use definite integrals to add up areas. And we're about to learn that even in cases where definite integrals for some odd reason don't work, and we'll look at that soon, this isn't what we do. We use something called the trapezoidal rule, which is just a better way to approximate. So I don't really want to focus on this stuff that you never use. I think it's good enough, and it's consistent with like the AP test. On the AP test, all you ever really do is just add up some small numbers of n where you can just add them up geometrically. So that's all I'm going to ask you to do is just stuff like this.
Don't really worry about that.
Well, no, I mean, you have to know how to do this. But I'm not going to have you build sigma constructions for this stuff, if that makes sense. I mean, like what I'm saying is, what if I gave you 30 rectangles?
Oh.
You're not going to add those up manually. Then you'd have to set up a sigma. You'd have to set up a discrete sum. And I just don't think that's. I don't think that's worth our time right now. We have limited time, and that doesn't seem like the right thing to focus on. So, okay, so there's that one, and I'll just show you that these are really same kinds of things. These other questions that you might get. I won't look at them all, but I'll look at a couple different. Oops. Okay, like these, same thing, isn't it? Right? If you can kind of, here, I'll read this so you get an idea. It says the table below shows the velocity of an object at each second as it moves along a track. So it gives us velocity versus, here's the velocity information, here's the time. Instead of giving it to us graphically, it's just giving it to us in a table. Estimate the difference traveled using 10 subintervals of length 1 second. Well, that's convenient because look, there's 1, 2, it gives us this data is represented in terms of second increments with left endpoint values. Okay, so we know that distance traveled is just going to be area under the curve, right? Right, under a velocity time curve. So graphically, what we really are doing is the same thing. We've got velocity and time, and if I graph this data, it looks like it just kind of goes like this, right? We're starting at 0, and then it just goes up a little bit. It goes up to 5, and then it goes up to 11. So it's just kind of going like this, right? And so if we were to use left endpoint representations, what are we doing? Well, there's the first one, there's the second one, there's the, etc., right? That's all you're doing. You're just going to add up a bunch of areas of rectangles to estimate the area under this presumably smooth curve. if we connected the dots. Make sense? So this is not really, I mean, it's not a hard problem. It's just, it's a little bit tedious because you got to add up 10 rectangle areas, but the widths are all one. That makes it a little easier too. See what I'm getting at? Okay. You might want to work through one of those on a practice test just to get an idea, but it's not hard. But it's good question. That's a question you'll see again in college, and it's, I mean, that's one that I'm confident needs to be on the test. What else? Oh, why do I keep doing that? Okay, find the general solution. Remember what a general solution is? That's just real quick. I mean, I'll tell you what. You guys raise your hand. Raise your hand if you want to see this one. I'll just go through them. Okay, let's see if people want to see that. All right. Okay, so if we've got something like dy dx equals 3x squared minus 2 secant squared x, and I want to solve the differential equation. Well, remember, solving a differential equation just means undoing the derivative, right? How do we undo a derivative? Antiderivative, right? So then we set up, now we know to set this up in terms of an indefinite integral. We used to call it antiderivative, same thing. So y equals what? What would I write? Okay, but I've got the integral of 3x squared minus 2 secant squared x dx, and now you guys are already jumping in to do the antiderivative, which is great. So then the antiderivative is going to be x cubed, right? Either by using our power rule for integrals or by playing calculus Jeopardy, either way. Minus, now what's this going to be? What's the antiderivative of secant squared? Tangent, yeah. So minus 2 tangent x plus c, right? It's an indefinite integral. They didn't give us any specific information there, did they? Right? I mean, we were not able to fill in that c. They didn't give us an initial value or anything. So we can't go back and find out what c is. Make sense? How can I check this? Take the derivative, and I better get back that result, right? Okay, good? Okay, same kind of thing. Oh, this is okay, this one here, though.
Only difference is you're solving to find
Exactly. Yeah.
what the C is too.
Yep, this one's a little different, isn't it? Okay, so.
I know it now.
Okay, and they're telling us that S of, I can't get that. S of 0 equals 7. So we do the same thing, wouldn't we? We're just going to do an antiderivative. S of t equals integral of 3 plus 4 cosine t dt. What is that? What's that indefinite integral or antiderivative?
3t.
3t.
4 sine t.
Yeah, plus. Well, okay, but remember now, if we're doing integrals,
Do an
it's a
antiderivative.
plus. Because you're asking the derivative of what is this, right? Is 4 cosine t. So we're just going to get 4 sine t. Because the derivative of sine is positive cosine, right?
Plus C.
Plus c, but we have this information.
You're gonna
Right.
plug, aren't you gonna plug 0 into t?
Exactly. So if we plug in 0 for t, what do we get? Well, that tells us that we get 0 plus 4 times sine t. What is sine of 4 times sine 0? What is sine of 0?
0.
0. So we get the answer.
7.
How'd they get 7? What the heck did they do?
C is 7.
Oh, because S of 0 is 7.
Oh, it equals 7, right, exactly, duh. Okay, so then we get 0 plus C equals 7, so C is 7.
You gotta plug it all back.
Then we plug that back in there. We solve for the constant by using our particular value or initial value, right? Plug that in, and we get the particular solution. Okay, make sense? Okay. Oops. Okay, same deal, a little easier maybe because it's not, there's no trig stuff in it, but same exact thing. Just says u equals 1 when x equals 1, and this is du dx, right? Essentially the same problem. Okay, these kind right here, remember these are just the ones where you don't really have to do any specific calculus. You're just, the point of this question is just to remind you about what a definite interval really is. It's just an area over an interval, right? So let's pick one of the harder ones here. What if we wanted to do,
G of x dx.
what if we wanted to do, okay, here's one. Let's do this guy.
7, 4.
This is a good one. So what if we want to add up the area under the curve from 4 to 7, and what we're given is, it's hard to see these things, but we're given up here that the integral of f of x dx from 2 to 4 equals 8, and the integral of f of x dx from 2 to 7 equals -4. How can I combine those in a way that's going to give me the area from 4 to 7?
Drag 4. That's what you do with it.
-4 minus 8.
Because 7's on top, so it's.
Okay, but how are you getting that?
That's 2 to 7.
Because they both have a starting.
Okay. Okay, and so now, and that's good. I think a lot of people are looking at this in terms of they're thinking of this in terms of what the graph would look like, which is excellent. You're thinking about it, if you look at these two graphs, I'm gonna take this area and then I'm gonna subtract this one, right? Because I've got all this and then I gotta subtract this amount from it, right? That's fine to do. There's another way to look at this though. We want to look at this in terms of our properties of definite integrals. We could also say, okay, well, this would equal the definite integral of f of x dx from 4 to 2 plus the integral of f of x dx from 2 to 7, right? Because if I stop at 2 here and I start at 2 there,
Just continuous, right?
it's just like I'm adding up a continuous area. See what I'm saying? If the upper limit of the first integral becomes the lower limit of the second integral, I can just join those into a single integral, right? Now, what does it do, though, if I reverse the order of the limits on this first integral? Yeah, it makes it negative, because we're adding up the area in the opposite direction that we started with. And if we add the area up in the opposite direction, remember that changes the sign. Okay, so this just becomes then -8 plus -4 is -12. Right? Is that, Lynn, you have questions? Does that make sense?
Yeah.
Okay.
Yeah.
And then they have some other ones down here, and these really aren't as big a deal. They have some of these down here where they do things like what about this guy right here? They have integral of g of x minus f of x dx from 2 to 7. Well, that's the only point they're making here is the very simple and obvious property of integrals that says I can split that up into two separate intervals, right?
It would be 2 minus -4. Right?
So it'd be 2 minus -4, exactly, yeah, right. So it'd be 6. Okay? And then if I multiply like a 5 by the g of x, I'm just multiplying that area by 5, right? Okay. Okay, now this one, only point I want to make about this is, notice the directions. You can do this using calculus, but that's kind of hard. It's unnecessary, right? If I want to add up the average value, and really, what is the average value of a function for integral? How do we define that? Area
Under the curve.
divided by,
Isn't it b minus a, or 1 over b minus a, or something like that?
well, kind of, but don't think of it as in terms of a formula, because you'll forget that. Just think of it in terms of what it really represents. The average value of a function, remember how we talked about that as taking our two-dimensional grinder in here and grinding this down and reshaping it to be a rectangle,
Yeah.
right? So if we reshape it to be a rectangle, it's still got the same area, right? But then rectangle has the area is easy to define. It's just width times height, right? Does that make sense? And the height would be the average value of the function, right? So then I'll ask you again, how do we define average value of the function? It'd be area divided by what? The width, exactly, right? Because if I reshape this thing to be a rectangle, right, then this is right here, by definition, this height, that we just changed the function from being one that changes to being a constant one with its average value, right? It's like cruise control versus put on the gas, put on the brake kind of a thing, right? So we want to know what would the cruise control be set on, essentially. So it's always just going to be the area under the curve divided by the width, right? So my point is then, in a situation like this, you could go through the somewhat tedious task of defining both of these lines as functions and doing a definite integral, but what's a much easier way to do
It's
this?
the area of the triangle.
Yeah, it's a triangle. Add up the area geometrically, and then just divide that area by the width, right? Okay, so that's sort of the point of a question like this is, sometimes it's better not to bother with all the fancy calculus stuff if you can just find an easier way. Just add up the area geometrically, because that's all a definite integral really is.
Sides equal,
What's that?
but sides equal.
Well, if you guys probably can't see this, if I make this bigger, maybe you can see. There. See now, pretty easy for us now to add up that area, right? We can see that it's got a base of 1, 2, 3, 4, etc., right? And a height of 1, 2, 3, etc.
Where's the width?
Well, it's there.
Oh, that's
To there.
the base and the width.
Well, sure, right? That's if we're adding up the average value of that function, the function starts there
Okay.
and ends there, right? Okay. Same thing here, right? Same exact idea. If we're trying to add up the area between the blue function and the x-axis, right? Adding up the average value. Really all I'm doing is just dividing area by width. In this case, how am I going to find the area of this thing?
What is,
Oh, is
what
that
half times pi r squared?
Pi r squared divided by 2.
Yeah, if I'm trying to add up this area right here, right? How am I going to find that area?
You make the rectangle,
Yeah,
and do that, and then subtract.
it's area by subtraction, isn't it? Okay, that may seem strange now, but that's preparing us for something that it's going to be ambitious, but that's kind of where I want to get by the end of the year. I'd like to get to some of these fancy three-dimensional problems where we do volumes by subtraction and stuff. But if we don't get to it this year, you're going to do it next year. So really all it is just this rectangle minus, the area of the rectangle minus, well, how would I define this area?
1/2 times pi r squared.
Yeah, just semicircle, right? And we know the radius, right? Okay. That gives us the area, so the average value would just be that leftover area that we found by subtraction divided by 18. Okay? Okay, same kind of thing, I'm just giving you more average value. This time I'm just giving you a function though, where you have to use calculus, right? It's not geometric this time, you're gonna add up this area with an integral. Same thing. Same thing. Same thing. Yeah, and you're not gonna get all of these are just different examples of ones you could get. So, you see what this is? You can't see this very well, but all this is saying is, if y equals 4x cubed plus 3x squared on the interval -1 to 2, if I want to find the average value of the function, it's just going to be the area, which is just this, right? You recognize that's just the area, right? That's what that means. That's the area under the
Wouldn't
curve.
you take the antiderivative of that function though, and then put it in there?
Well, that's what we're doing. That's what that means,
Oh, see, okay.
right? Okay, divided by what? Yeah, good. Divided by 2 minus -1, so divided by 3. Right? Good. Okay, this is just asking you to, nothing more than just asking you to do a definite integral. Just, just get, what's the area under the curve? That's all it's asking you for. These are the ones you're probably the most, no, you won't have a calculator.
You want to? Or you don't?
You know, you can't on this part of the test.
Oh.
There's gonna be another part where you can just put all this stuff in your calculator and it's really easy. Same thing here. And you guys have had this is what you've had probably the most practice with.
Oh, yeah.
Most recently is doing this stuff. Okay, what else is weird though? Let's look ahead a little bit. Okay, right here. Let's take a quick look at this one. Oh, never mind. Same stuff. Okay, real quick though. Okay, when I'm doing this definite integral, when I'm doing the antiderivative, only tricky part of this whole thing probably is just going to be square root. How do I deal with that?
Times the 1/2 or the 1/2 power.
X to the 1/2 power, right? Okay. We good with that? Okay.
You use.
Same stuff. Same stuff. Same stuff. Now these, I put through a couple of them on there that are a little bit harder. Just one real quick. I'm not gonna do the problem, and I don't really want to because I don't want to do too much of this. I'd like you guys to. I can't even read that. Is that 1 to -1? It looks like. Okay. Let's just talk about this for a second. What am I going to do to this to be able to take an integral?
Expand it out.
Yeah, I got to be able to expand it out, don't I? So I've got to expand out the integrand, and then I'm just going to get a polynomial, which is easy. I'll just integrate term by term and evaluate the function at -1 and subtract from that my antiderivative evaluated at 1. Right? Right?
Okay, when do you?
Do you have questions on that?
I got a question.
Yeah.
When do you divide by the b minus a? When do you?
Well, that's only when you're trying to find an average value.
Okay, so
Yeah.
that's average value.
Yep.
Can you run this again, this
Right, of this thing? Yeah, okay, so what we're gonna do with this, we're going to, this is too complicated for us. There's no antiderivative rule for something that complicated, but if I just expanded that out, I'm just gonna get 81t squared plus et cetera, 3 terms, right? Each one of those, let's just look at the first one. I'm gonna end up with the antiderivative, whoops, +1 to -1 of 81t squared plus et cetera dt. Well, the antiderivative of that would just be 81 times t cubed over 3, right? Everybody see that? So, so 81 over 3 is 27. So we're going to get t cubed over 27 plus some other stuff. evaluated from 1 to -1. So I'm gonna plug this one in first and subtract from that the value at this one, right? And this just boils down to, remember what this is. This is just our fundamental theorem of calculus. This is the one that says the definite integral equals the antiderivative from A to B, which really just means the antiderivative at B minus the antiderivative at A. That's the trick, in other words. That's just taking a definite integral. Okay? Make sense? To me, I would predict for you guys that even though this problem arguably is a harder problem in a way, because you have to expand stuff out, I think these are going to be the easiest ones for you, because you've had the most practice with them. Okay, now here, let's look at this. There's a little different kind. So these are the ones where if you're given an area function, so y equals t cubed minus t to the 4th dt from 4 to x, and we want to know what's the rate of change of this area function. What's dy dx? This is that second fundamental theorem shortcut. What's the answer?
It's just the same as the derivative cancels out, or the dt does.
So what would I write down for my answer?
Just be the answer antiderivative of the function.
X cubed minus x raised to the 4th.
Say it again.
X is gonna be x cubed minus x.
Exactly.
minus
Yeah, the answer is x cubed minus x to the 4th,
Oh,
Yeah.
okay.
right? By the second fundamental theorem,
So you take the derivative and derivative cancels.
right? Right? Okay, and that's that sheet I gave you.
Yeah.
This is an easier version, but you know, what if this had been, let's just say hypothetically, this had been an x squared? What would our answer be?
That squared.
Then I'd get, that would be an x squared, and that would be an x squared. So that'd really be an x to the 6th then, wouldn't it? But I'd have to multiply the whole thing by what?
X.
By the derivative of that.
Yeah, it's gonna be 2x. So it's gonna be 2x x cubed to the 6th minus squared.
And just real briefly, remember what our justification for that is. If we're trying to find the rate of change of the function, well, the rate of change of the function only depends on the height of the function, right? Which is this, right? And if the top of the function is not x itself, then as x increases, remember that as x increases, x squared is going to accelerate. So as x gets bigger, not only are we adding up area, the height is determined by the function, how high the function is, but we're sweeping out area at a rate that's going to be greater because we're sweeping along horizontally faster because of that. Well, how much faster? 2x, right? Right. That the rate at which the rate of change of x is 2x. That's what that derivative is. Right. That's kind of a tough thing to conceptualize, but try. Think about that a little bit. When you go to bed at night, think about that. That's just when sometimes people do the best thinking. Try to wrap your brain around. I mean, these problems are easy. In terms of being able to do the problems algebraically, they're easy. But see if you can get a conceptual handle on what's, challenge yourself to do that. If you can make a picture of how do you think about that. Same thing, right? Same stuff. Okay, how about this one? Find the area of the shaded region. Okay, now how are you going to do this one? It's not hard, but you got to, I think to do these kinds of problems, you have to understand what calculus is really doing here. If I want to add up that area, what would I do?
Are you taking two different integrals?
Yes, you are.
So
Nice.
Yeah, good, the left function and the right function. It's like we're gonna split this thing down the middle. And from 0 to 2, we're adding up the area under the curve y equals 5x squared.
And on the right side, you're doing the other one.
Exactly. Right, and then we're just gonna, by adding up those areas, does that make sense?
Really, that's all you have to do?
That's it,
Wow.
that's it. Okay.
Hang on now, hang on, let me write that.
So if you're adding up an area under a piecewise function like this, you just have to add up the areas under the individual pieces separately and just add them up. Okay, wherever the function changes behavior. Okay, so I wanna make sure I get through all this stuff. What about this one? This gets us ready for some cool stuff in the near future. So if I want to add up the shaded gray area, how would I do that?
Two different.
Area by subtraction. This time the bottom subtraction though is going to be an actual definite integral, right? Okay, and I think that takes us right up to the end. I think that's where we're right at the end there. Okay.